Well, good morning, ladies and gentlemen. Welcome to another meeting of the Kent, Surrey, Sussex branch of the Royal Society of Biology. Good morning. It's an unusual time for us to have a lecture, but as our contact this morning is in Australia, so I'm sure you will understand. Now, I'm Graham Godfrey, the Deputy Chairman of the branch, and with me today are David Lewis, who is our Secretary, and Karen Patel from the Central Office, who is coordinating everything. Now, today we are very fortunate in welcoming our speaker, Professor Lidia Morawska, who is based at Queensland University of Technology in Brisbane and is director of the International Laboratory for Air Quality and Health. She has also joined the University of Surrey to work with the Global Centre for Clean Air Research, and has recently been elected a Fellow of the Australian Academy of Science. She's an acknowledged expert. She's a physicist, not a biologist. She's a physicist whom we welcome very much, of course, into our fold. She's an acknowledged expert in the field of radiation, environmental and atmospheric physics, and her recent work has been focused in the interdisciplinary field of air quality and its impact on human health, with particular emphasis on the spread of airborne particulates. Her most recent work has been on the transmission and spread of virus-laden particles, respiratory aerosols, I should say, which is oh so relevant to our present predicament. Lidia has been instrumental in changing the World Health Organization's policy with regard to airborne disease transmission, and now it gives me great pleasure to welcome her today to explain to us how disease is spread in this way. Over to you, Lidia.
Many thanks, Graham, for introducing me, and many thanks for inviting me to give this presentation. When we were exchanging emails about the topic title of the presentation and what I'll be covering, you suggested lots of aspects which the society might be interested in. So I thought I'll talk a little bit about all of this, just to give you an idea, of course, from the physics point of view. So I'm glad that you stressed this, that I'm a physicist, so you don't expect me to talk about biology, but hope there'll be enough leads to physics. So I'll talk about the world of airborne particles, generation of particles during respiratory activities, characteristics of these particles, dynamics of the particles in the air, and then also inhalation of the particles, what's coming as an evidence from the outbreaks and how we model the outbreaks, and finally mitigation and mitigation beyond COVID-19. Now, the world of airborne particles has been something which excited me since I was a postdoc in Toronto, which was a long time ago. And when I discovered the world of what's now called ultrafine particles, the smallest particles in the spectrum of the particles in the air. Now, to just bring you this concept of particles in the air, you probably realize this, or maybe don't think about this normally, that's how it is. And I start with saying, well, if we compare these two objects, sand grain and a boulder, well, of course, they are completely different, many orders of dimensions, difference in sizes. We would use different instruments to measure them if we wanted to different impacts. But if you compare from the microscopic world, a particle emitted by a petrol exhaust vehicle, for example, and a dust particle like dust on the ground, the difference in terms of sizes is similar to the difference between the sand grain and the boulder, which immediately gives you an idea about the complexity. We don't see any of these objects, neither dust nor petrol particles, but yes, there are orders of magnitude difference between them. And then the question is, well, we measure particles, but which aspect of the particles we measure? Now, I'm not going to go into detail in this, but PM10, PM2.5 is how regulatory particles are measured, mass concentration of particles smaller than 2.5 or 10 micrometers. But we can measure something different. We can measure ultrafine particles, which are smaller than 0.1 micrometer, very different measurements. We can measure just black carbon. We can measure metals in particles. We can measure so-called secondary organic particles, which are usually liquid, or we can measure desert dust. Or finally, we can measure biological aspects of the particles. We can't usually measure all of them. So what is what we measure? Now, another issue in relation to the pollutants in general, and specifically particles, is whether they are primary and secondary. Primary pollutants are those directly emitted from the sources, being these vehicles or industry or natural sources, and this cloud where are the primary pollutants. But once they are emitted and once they are in the air, they interact with each other, they are subjected to solar radiation and therefore photochemistry taking place. And then there's a whole suite of so-called secondary pollutants. One of the most best known of them is ozone. So the complexity of what's happening in the air is quite immense. And as I said, we usually can't measure all of this. Now, on the top of this then comes another complexity when we are talking about biological particles, and I refer to them particles. And again, if we compare the sand grain and the boulder with a virus and a pollen particle, the difference in sizes, it's again orders of magnitude. So if we are first to capture these particles as physical objects, again, we need to use different means for doing this because the dynamics is different. And then in a different way of comparing these different objects in the air. So if we compare this big circle, this human hair, and then bacteria, well, of course, they have different sizes, but the biggest one up to about 10 micrometers, road dust, up to about 5 micrometers, coal dust, up to about 2 micrometers, virus up to about 0.4, and vehicle emissions up to say 0.2, but the majority of them are much smaller than this. So this gives you an idea of overall complexity of these things. Now, for the completeness of this discussion, I'll also mention this issue: is it aerosol or droplet? And I'm glad that you mentioned, Graham, in your introduction, that issue. Now, in aerosol science, that's where I belong, the definition of aerosol is assembly of liquid or solid particles suspended in a gaseous medium long enough to enable observation and measurement. And droplet is a liquid particle. Therefore, it has nothing to do with the sizes of this object, of the particles. It's just the composition, liquid versus solid. It's a completely different situation in medical sciences, where they call aerosol as smaller particles and droplet as larger particles, with division being at 5 micrometers, which from the physics point of view doesn't make much sense because there's no natural division. I realized that how the different areas were entrenched in their definitions and how difficult it was So my approach now is to, well, first of all, don't worry about these differences when I talk to any medical colleagues, and I just refer to them particles because they are particles, and this normally avoids any problems. So with this general introduction about what's in the air, I'll now move to the particles from human respiratory activities and aerosolization of these particles. How does it happen? So particle aerosolization in expiratory respiratory activities results from the passage of an airstream at a sufficient high speed over the surface of a liquid. And where is this liquid? The liquid is in our respiratory tract and in different parts of the respiratory tract. I often say that the process is very similar to what happens in an old-fashioned perfume bottle or a nebulizer. I'm sure many of you have used nebulizer. The complexity is that because there are many different parts of the respiratory tract, it's like many different nebulizers operating there. And in fact, some of these processes are even somewhat different than just to nebulization or aerosolization. So this multiple processes of particle generation could be summarized like this. If we start from the bottom of the respiratory, lower part of the respiratory tract, so here we've got the process due to fluid blockages, which forms during exhalation, and then they burst during the subsequent inhalation, producing particles. These are usually the smallest particles. Then there's a slightly different process in the larynx, and here the particles are generated during voicing, during vocal voicing and vocal cord vibrations. And yet another process, a bit different, and actually several processes occurring in the mouth, and here the aerosolation is because of the interaction during speech articulation. So we've got particles generated in different parts of the respiratory tract during different respiratory activities. And then a complication, another complication of this is that after the formation, the particles already start changing even before they leave our mouth or nose. And in particular, traveling, for example, upwards, they change size distribution because some of them are deposited. There was a fascinating paper published last year in Science about surface deformation and how these bubbles collapse and then form new particles, smaller particles, and how this generates the formation of new particles. So this is the complexity of what happens there. Some years ago, when we started working on this topic, and this was, I'd like to add, soon after SARS-1, that was when particle from respiratory activities was added to our portfolio of particles which we worked. So here is the bronchial fluid film burst, and it shows how it occurs. So we look at the top. So this is airflow going this way, and we can see how the passage contracts and how eventually it's completely blocked. And then when the airflow in the other direction, then the particles formed. Now, the point is that we cannot measure these processes directly because there's no way we can measure anything directly in the respiratory tract. We can model them, we can simulate them, and that's how we learned what's happening there. Now, I'd like to say also a few words about detection of these particles. At the beginning of the pandemic, many colleagues from different areas, particularly medical areas, contacted me saying, well, can you bring your counter and measure this and this? And I was saying that it's not as easy as just bringing a counter and measure particles from respiratory activities. So the way we did this was the design which we came up with when we started this line of research. So what we have here, we've got person sitting in this flow tunnel. The person is well, breathing, speaking, coughing, singing. You'll see in a moment what's coming out of this. air is flowing from the back, it is straightened, filtered, so it's just clean air. And we have a line of different instruments connected and sampling from downstream of this process. Now, the reason we wanted to do it like this is because we were able to measure particles of exact size, of exact age. As I'll explain in a moment, particles change so fast due to evaporation that if we, let's say, sample from an experimental chamber in which the person would be seen, we would have mixed of old and new particles. This way we knew exactly what we were measuring. But then, because of the different sizes that I generated, we needed a different set of instruments. There was no one instrument which could measure all of this. But there are other instrumental techniques, and that's, for example, one from a paper by Zayas and colleagues when they use this setup and open badges for specific focus on cough. And this was laser diffraction system where they were able to actually measure, not capturing, but measure a larger size range of particles. But then there's another issue. If we want to capture the particles for specific measurements, for example, of biological properties, and we need enough of them, we need to do something different. And that something different in this case, what a system which we designed was a rotator. So the person was exhaling into that rotator, it was rotating, and this way we were able to keep the particles in the air. And this could be to achieve higher concentrations if we needed to, or to test for how long the pathogens would stay viable. And that's, for example, the way we did such measurements for Pseudomonas. But this technique is not suitable for fast changing processes. So I hope this gives you an idea about the complexity of these measurements, and they need to be aligned exactly what we want to do. Now, despite all the complexities of not being able to measure directly in the respiratory tract and measure in full stop, we have a reasonably good idea about the characteristics of particles emitted from respiratory activities. So this is an example of size distribution from that tunnel which I showed you first. So what we see here, first of all, we see that the range of particles, the particles range over several decades of sizes. We also see that these smallest particles are more, the majority of them are smallest because the scale, vertical scale is logarithmic. So that's where the majority of the particles are. Of course, there are particles here, but very few particles in the larger sizes. Now, this, as I mentioned before, these particles of different sizes come from different parts of the respiratory tract. So this is that VFB mode, as we called it. And interestingly, this was considered the way H5N1 was generated because this was the location of the virus in the respiratory tract. Now, this bigger mode is from laryngeal vibration. And then the largest one in terms of sizes, oral speech articulation. And interestingly, this was considered the source of H1N1 because, again, that's where that virus was located. Now, something which I'd like to mention, it is not that this is just from one instrument and, okay, we've got the size distribution. There were 10 processing steps to put this and assemble this distribution together. And also, please note the scale. Here we are talking about particle number concentration. Now, logarithmic scale, but particle number, not volume, not mass, particle number. Now, what's coming in terms of from different measurements, and this is that going back to the experiment by Zayas and colleagues, you see a different distribution here. First of all, they measured much smaller particles as well. It appears that there are no bigger particles, but they were the bigger particles, but because there were so many of the small particles which we didn't measure, therefore the larger particles are not visible in this scale. now, and this scale is also particle number here. Now, there are many more particles in the smaller size which we measured, but the point is that these particles are too small to actually, some of them are too small to carry a virus, because many of the viruses are much smaller than this. But as I said, these are all the particles generated. Now, what's the concentration or relative concentration of particles from respiratory activities? Again, this is from our experiment. So what we see here are particles generated from, the first one is breathing, nose and mouth. Then the second is voice, counting voice. Now, the biggest concentrations are emitted during singing activities. And this is consistent with measurements conducted by others. The group of Asadi and colleagues conducted similar measurements using similar set of instruments, aerodynamic particle sizer. And again, the relative concentrations of particles generated between breathing and speaking loud and quiet was quite similar to what we did. So this is in a way quite consistent. So if we were to summarize what's generated from respiratory activities in terms of all particles, is that the majority of particles are smaller than 1 micrometer, and the vast majority are smaller than 10 micrometers. The point is that such particles are light and therefore can stay suspended for a long time, and all respiratory activities, including breathing, contribute to generation of particles. All right, now you can ask a question, okay, this was just all particles, but where are the pathogens in these particles, and in particular viruses? When we talk different pathogens have different sizes. The size of SARS-CoV-2 naked virus, as we call them, is about this 0.012 micrometer. But the point is that the viruses are not normally naked or emitted naked. They are emitted in virus-laden particles in the process of aerosol formation, which means that the particles carrying the viruses are bigger than the naked virus, because they contain also water, mucus, salts, and whatever else is on the surface. So they are bigger. The question is how much bigger? There were measurements, for example, conducted by Santarpia and colleagues, which showed, and I'll show a graph on this in a moment, that the majority of the particles are smaller than 1 micrometer. So that's what, in general, we can conclude that the majority of the particles are containing this virus, SARS-CoV-2. It means mid-submicrometer range or slightly bigger. Now, that was an interesting experiment conducted by that group of Santarpia. This was conducted not in an experimental setting, but in a COVID ward. And that's what that's one of the main graphs from their measurement. Now, they use the same instrumentation in terms of measuring all the particles, and these are the solid lines. But they also used a NIRS sampler of 3 stages to measure biological viral content of the virus. Well, first of all, doing it this way, they included all respiratory activities, because the patients in the ward, they were speaking, they were coughing, they were breathing, of course. Also, this is required several steps in data processing. Now, and in this case, please mention this, notice the scale again. Here, we are talking about mass concentration. What I presented before was number concentration. This looks bigger because it looks like this, that's much more particles in this larger size range. It is because it is mass. Now, particle mass is proportional to radius to the 3rd power. So a small number of large particles contributes significantly to mass. So it's not that it's just different situation, it's just presentation of mass or volume versus number. Now, what's the most important here for our discussion is that the highest viral load, which they detected, was in this smallest stage below 1 micrometer. And there were other measurements like this as well. So if we were to summarize, where is the varus in this particle? So in relation to this varus, smaller particles contain higher loads. These particles come from the deeper parts of the respiratory tract. Larger particles, less virus, originate from the mouth. And breathing and speaking is the main source of these particles. So we know now what's coming out in terms of particles and containing the virus. What happens to them when they enter into the air? There are several different processes. The fastest and perhaps the most important in terms of the fate of the particles is evaporation. Now, some time ago, I did this simple simulation looking into the time of evaporation of water. That was the title in the paper, water droplet evaporation. And I looked at the sizes of 1, 10, and 100 micrometers, different relative humidity, and the last one containing also a salt solution at the concentration which is typically in our respiratory fluids. Now, what you can see that the evaporation time, and evaporation is when the line stop. It is very fast. It's a fraction of a second for 1 micrometer and for 10 micrometers. Now, if the particles contain like salt, of course, there's that residue left, but water content evaporates very quickly. So this process is very, very fast, almost instantaneous. Now, of course, the process of evaporation is more complicated for actual particles from respiratory activities because of the all complex content they have. But again, it's a very fast process, and that very fast evaporation to about 20 to 40% of the initial size. So the bottom line here is that what we measure is usually already, and I left the term what's often called droplet nuclei. So basically what's evaporated to the stable particle size. It doesn't mean that they completely evaporated. There's usually some water content left, but they stop evaporating anymore. Now, the next issue is that conception often that particles fall. So they are emitted, exhaled, and they fall. But the reality is that we are talking about very small particles, and the majority of them, they float in the air. So this is a summary from Wells, 1934. Wells was kind of like father of this area of science. And he compared particle diameter with the, in quotation, my falling time. Now falling because not only gravity taken into account, but drag and other processes acting on the particles. So basically what we can see that for the particles of our interest, 1 micrometer, 10 micrometers, that falling time, which means the time they float, are suspended in the air, it's very long. So they really stay in the air. And of course, on the top of this is the fate of the virus in the air, and whether it remains active or not, but I'm not going to talk about this aspect. Now, so this is another presentation of the evolution of, in this case, of cough or sneeze cloud, according to this paper. And I like this because it shows what's happened. So this is the phase. Here is that cloud emitted. The cloud is warmer normally than the air, and warmer air, the path goes upwards, while that small number of large particles settle, but the rest, the majority of them, just stay in the air. So in terms of particle dynamics in the air, we can summarize it like this. There's gravitational deposition of large particles, that small number of particles, flow dynamics of small particles, and that's the majority. And there's also removal by ventilation, as well as other processes in indoor environment, but ventilation normally is far more important than any other processes. And the level of understanding of this is very good, quantitative, very based on empirical studies and modeling. So they typically ask questions. How long will virus-laden particles stay in indoor air? And my response to this is, as long as the forces acting on them will keep them in the air. Minutes, hours, it depends. And the second question, how far will virus-laden particles travel in indoor air? And again, as far as the air flow will take them. Meters, tens of meters, well, potentially hundreds of meters, but normally indoor environments don't have hundreds of meters. But they can travel with the flow quite far. So the last point of the journey of these particles emitted is then deposition in the respiratory tract of those who inhale this. Now, the complexity here is all what affects this deposition. So it's the particle size and size distribution, as we've discussed, density, shape, surface area, whether the particles are hygroscopic or hydrophobic. Then the anatomy of respiratory tract, and we are all different, as we know, and this is a very significant factor. And finally, the physiology, which is air flown pattern and breathing pattern. So there are huge variation between individuals in terms of deposition. And this is something, again, we cannot measure directly. We can do all kinds of things. We can, for example, label the particles with radioactive technetium, radioactive substance, and then see where they are. But we really don't have no means of measuring what directly in the respiratory tract. But what we do is we do modeling, and there are very good models which represents, in particular, total deposition quite well. So what we have here, it's particle diameter and deposition fraction in different parts of the respiratory tract. So the blue line is total, and then tracheobronchial, headways, pulmonary, and so on. There are different physical processes which affect deposition dependently on the size and weight. So diffusional processes are the most important in the lower particle size range, and impaction and interception in the larger particles. Now, of our interest from the point of view of particles with the viruses, this range is the most important because that's where the particles are. So this is where these particles deposit. So we can say that the level of understanding is we've got well-established models validated by empirical studies, but for total deposition. For total deposition is that we compare what's inhaled, what exhaled, but doing it for the regional deposition is basically not possible. It's all modeling. Now, what is it doing now? Right. Okay, so with this understanding, let's talk a little bit about what's airborne infection transmission. Airborne transmission is inhalation of virus-laden particles anywhere in the space. So in this diagram, we've got the situation. This is infected person, and then susceptible people can be anywhere at a distance from that person. And of course, here in the proximity to the infected person, to any person, the dynamics of everything is very high. We have particles of all sizes. The larger particles deposit on the ground, but then as we go with distance, it kind of settles. We have a large number, but of smaller particles. So really, airborne transmission is often people understand as transmission in the longer distance, but it is really inhalation of particles at any distance from an infected person. So in terms of physics of respiratory infection, like now summarizing all of this, We've got quantitative evidence of characteristics of the particles, virus-laden particles from human respiratory activities. We know what happens to the particles in the air, transport and removal, and we understand the position of particles in the respiratory tract upon inhalation. So now we can ask, okay, do we have such evidence available for each outbreak? Because this will tell us basically about everything about the outbreaks. But the problem is that this we don't, because the complexity of the processes which I just described, it is not something we can measure. We have for the outbreaks, because there's no one during the outbreaks. It is not known that the outbreaks would occur. So we normally, in real life situations, we have just a few of these parameters, but we don't have all this to properly model from the first principles. But we have evidence from the outbreaks of different type, and this is a different type of modeling which we use to quantitatively assess what's happening. One of the first modeling which was published was of this event, Skagit Valley Choir outbreak in the United States, when where 53 out of 61 participants were infected. I was involved in modeling with colleagues from Italy, Luca Stabile and Giorgio Buonanno. Now, I'm not going to talk about the details of this modeling. I'll come back to this in a moment. But basically, what we were able to quantify was quanta concentration emitted and exhaled, and probability of infection for the assumed quanta. And the point was that the modeled results agreed very well with the outbreak data. Then later was another paper published where we published in modeling slightly different way. Now, different modeling was conducted for this case, and this was the Diamond Princess cruise ship. And here the researchers looked at the transmission mode and viral source. And in the transmission mode, they looked at what they called short range, which is droplets and aerosols, which is smaller and larger particles, and long range, just larger, the aerosols, smaller particles, and fomites objects. And from this, the estimated infection contribution, they concluded that the larger was the aerosols, what they called, and the least important fomites. In terms of the viral source, by far the aerosol, the smaller particles were more significant. Now, yet different modeling was presented here, where the researchers looked at 12 documented outbreak data, and they modeled the results. So what we have here is the in blue modeled and in red documented. So the model assumption was that all cases were caused by long-range transmission, which means that smaller particles. And interestingly, the agreement was in 9 cases out of these 12, in a way supporting the case for airborne transmission, which obviously then leads to the conclusion that airborne transmission is very significant, perhaps the most significant, I'd say the most significant, and must be mitigated. So now let's talk a little bit about that mitigation. What does it mean? I'll focus here on building engineering controls. We've discussed this in our paper last year, how can airborne transmission of COVID-19 indoors be minimized? And among the engineering controls, we have ventilation, sufficient and effective, avoiding air recirculation, so there's another aspect how ventilation system works, particle filtration and air disinfection, avoiding overcrowding. I'll focus specifically on ventilation, sufficient and effective ventilation. Now, what does it mean, sufficient and effective? Sufficient, in a simple term, means enough of it, and effective means everywhere in the room, in the space, and airflow not going from one person to another. This wouldn't be important in relation, let's say, of carbon dioxide, which we exhale, but in relation to infection transmission, this is very important. So on that paper, which was, well, that was called Open Letter last year, in the top panel, there's definitely not enough ventilation because the particles exhaled by this person are everywhere. And on the bottom, it's a bit better, but still it's not everywhere in the room because the particles are in some places. So, sufficient ventilation. What does it mean, sufficient ventilation, in relation to infection transmission? Of course, there are ventilation guidelines, standards, and so on. Can we use them for controlling of infection transmission? For example, guidelines for removal of CO2 exhaled by occupants. Now, the issue is that it's not that simple, because we need to use for this what's called risk assessment models and tools. What does it mean? It relates to what we to the infectious quanta. That's how we quantify what's emitted in terms of the viral or bacterial content and what's inhaled. And the quantum is the dose of infectious airborne particles required to cause infection in 63% of susceptible persons. This is Poisson's distribution. Well, it's a convention. We could say infection of 100% known, that's the convention. Now, what does it depend? Emitted quanta, what does it depend on? Well, depends on the location of the pathogen in the respiratory tract, and that's what we've discussed before. Physiology of the respiratory tract, stage of the disease. With the stage of the disease, the virus can move, change the location. Type of respiratory activities, as we've discussed, vocalization results in more emissions, and the virus itself. So it is quite complex to be able to quantify what is the infectious quanta for a particular pathogen and how much is emitted. But things like this have been done, have been modeled, and the traditionally used model is the Wells-Riley model. I'll just bring this is the very simple equation. I'm not going to talk about any more equations, but just to show you what elements come in this kind of modeling. So first of all, I, the number of infectious source cases, infected people, the number Q, the number of infectious quanta produced per source case, that's what we've discussed a moment ago, the average respiratory ventilation rate of susceptible person, that's a person who inhaled this, the duration of exposure, this is a critical factor, and the volume of infection free with, well, clean or outdoor air. So this is the basis for any risk assessment calculation. This then gets more complicated, but as I said, this is the starting point. And assessment like this have been done for a long time. We did such assessments some years ago with colleagues here in Brisbane, and this was ventilation and infection risk in this particular Prince Charles Hospital lung function laboratory for 15 and 45 minutes occupancy. And we did it for 3 types of diseases, influenza, tuberculosis, and rhinovirus. And what we can see here on this diagram is that, so we've got outdoor air exchange rate per hour on the horizontal axis and infection risk on logarithmic scale. So as expected, the risk increases very rapidly with the increase of outdoor air exchange rate. And of course, depends on the specific pathogen and the infectious quanta. So things like this can be done and have been done for quite a long time. During this pandemic, that was these models and tools for risk assessment mushroomed. There are many of them. We've developed with colleagues what I presented you before that on that Skagit choir. We've used this airborne infection risk calculator, which is on our website. It's the 3rd edition of this already. And it's been used for many purposes in many countries. So we've recently published a paper on ventilation procedures to minimize the airborne transmission of viruses in schools. I'm not going to go through the details of this diagram, which is quite busy, but it goes through the process of what needs to be done, that assessment in schools with mechanical ventilation, with natural ventilation. So step by step, dependently on the conditions of the number of people, of the quanta emitted, and the time spent, we can calculate the risk and then decide on the risk which we can agree upon. And actually this approach, and including this diagram, is already used by the equivalent of the Italian CDC, Center for Disease Control. It's called differently, to do risk assessment. And others have done similar things. So in this case, Bazant and Bush calculated, provided a guideline to limit in the airborne transmission of COVID. And here they, on the horizontal axis, we've got time without masks and the occupancy time, and then they came with this assessment. So when it is unsafe, and these parameters, occupancy time and mask, come into unsafe, natural ventilation, safe, and so on. So again, these things can be done. So in summary, assessing the requirements for sufficient ventilation is relatively easy. We have tools for this. Now, but the assumption is that there's uniform mixing of the air, which is not always or rarely the case. And if air is not mixed uniformly, so of course that's a problem, because we don't capture what happened. And one specific issue here is close proximity, because if we are in a close proximity to an infected person, then this concentration is much bigger, and this is before really the ventilation had a chance to distribute it evenly in the space. Now, what does it mean, close proximity? Well, different jurisdictions have different definition about this during the pandemic. Is it 1 meter? WHO has 1 meter, 1.5 meter, 1 kangaroo apart. If you are in Australia, so there are signs like this: keep your distance, and it's got to be 1 kangaroo apart. Well, the point is that, as I mentioned before, there's no division, it is a continuum. So we can't say it's exactly this or this, it's a continuum. And closer to the source, to any source, in this case to an infected person, concentrations are higher, which means shorter exposure time lead to infection. If we are away from the source, concentrations are lower, and therefore it is longer exposure time, which leads to infection. So these parameters come together, and this close proximity is something of particular significance. Now, this is another paper which we've published with the same group of colleagues, where we looked at used this infection risk calculation models. And in this case, we looked at the really close distance. Now, the definition in the from social sciences is that we've got intimate distance, that's red line here, personal distance, and then social distance, which is bigger. And then on the bottom diagram, if you look at so we've got the risk of infection and the distance, and you can, and the time. So this green line is speaking, so it's 10 seconds of exposure, 1 minute of exposure, and then red is 15 minutes of exposure. So, for example, in relation to speaking at a distance of 0.6 meter, so this for 15 minutes, the infection risk is about 50%. If we come close, it's about 100%. So from analysis like this, you can look where you are in terms of distance time to be infected. Now, this calculation was done for the alpha variant of the virus. If we talk about delta, the only difference is, in terms of delta, is that it's significantly more of the virus emitted, which means much shorter exposure time will lead to infection. But as I said, these things can be done, and it's being done in terms of calculations. So finally, what's effective ventilation? And we can get an idea about this based on this paper which investigated the outbreak. It was last year in a Guangzhou restaurant, which looked like this. Now, this is an air conditioner which turns air around in this part of the room. It doesn't bring fresh air, just turns air around. The infected person is here, and people in this part of the restaurant were infected. No one in this part were infected. So the conclusion from was that it is the flow direction was a problem. Of course, there was not sufficient supply of fresh air, but this unidirectional flow, which means ineffective ventilation, was a problem. Now, this leads to contradicting requirements and misconceptions. So at some stage, somebody asked me, that was from Spain, saying something like this: the university advises to avoid cross ventilation during any lectures, to avoid this kind of unidirectional flows. And the recommendation is to avoid opening opposing windows or doors during classes in order to avoid air currents. Not to do this, what happened on the previous slide. And so the rationale is that such currents can transport aerosols from one person to another. But if we don't open these doors or windows, the ventilation will be significantly reduced, which means much higher risk. So if we open this, that cross current potentially can infect people on the line of the current, but if we don't open, the whole room can be infected. So what to do with this? We've got models like, for example, computational fluid dynamics modeling, where we can do a very, very detailed modeling. Would this provide us answer about flow direction? It would for specific indoor spaces, but we need general solutions. We can't do this kind of modeling for every room, every classroom, every shop. We need some general solutions. And this is where the complexity still is. So in summary, assessing the requirement for effective ventilation, which is based on the airflow, is still a challenge, and the issue how to generalize so we can have outcomes without detailed modeling for every space. So the last part is the future beyond COVID. In May, we've published with colleagues this paper, A Paradigm Shift to Combat Indoor Respiratory Infections, not just COVID, but indoor infections in general. And to start, what we suggested, we need a paradigm shift. It's how buildings are designed, how they are equipped in terms of this engineering solutions of ventilation and providing airflow, and how they are operated. Now, to minimize all air risks, including airborne infection transmission. What does it mean, all air risks? Now, I started from that everything which is in the air. So the virus, the pathogens are not the only particles, not the only pollutants in the air. So really, the situation is much complicated. So mitigation of all air risks. Now, I was talking here about this mitigation of airborne infection, but we also have anthropogenic sources operating in the rooms, being combustion sources, being some kind of burning or something, smoking or whatever it is. Now, we've got pollutants coming from outdoors. Like right now, there are so many places where fires are raging and that smoke gets inside. So this has to be prevented. So, okay, let's close up the building completely from this point of view. If we do this, and that's what's been happening, then dampness and what follows is mold can develop. Then, of course, the issue is of thermal comfort. All these things have to be brought together, and ideally at the building design stage, because retrofitting, taking all this into account, is much more complicated. At this time of the designing of heating, ventilation, and air conditioning system, equipping the buildings with the operating property, and importantly, considering energy demands. It is not just, okay, increase ventilation and everything will be resolved. because this is a huge energy draw and we cannot afford that the buildings draw more energy, because as is, about 30% of energy is consumed by buildings in general. So this is a complexity in all of this, but well, we are flying rockets to Mars. We can technologically resolve this. And again, in the same paper, we've briefly discussed that solutions are already here, how we can design building considering the occupancy. So in terms of what flow we need of airflow, we need to consider how many people are in this space and what they do. We can also have it demand controlled if we have fewer people. We can have lower airflow, which means lower energy consumption. If we divide airflow, we can have even less flow and provide the efficient removal, like here, the flow is coming from two directions at the bottom going upwards, then less ventilation is needed. And in situations where people are stationary, that's personal ventilation and even less flow is needed to provide the same or to achieve the same objectives of ventilation. So we have many solutions. It is just wanting to put them together and putting them together. Now, one other system issue is that as is, we have absolutely no idea what is the situation with air quality in our buildings. Do you know what's ventilation in the office you are? No one knows. But what we are saying is that we have the right to know, and then displaying this state of indoor environment is very important, because it would help developing awareness and keep building operators accountable. Now, what can we display? Well, typically temperature and relative humidity is displayed. But there are systems like this one, and this is a photo which I took a few years ago in a research institute which I visited in Germany. A system like this apparently I use in German schools. So this is a CO2, what's displayed here is a CO2 concentration, and it's already quite high, and I was surprised that it got that high during that meeting. But well, you don't need to know what's high in terms of concentration. You look at traffic lights. So as you can see here, it's not all that well visible, but you can see that it's already in the top amber, so it's going towards red. Red is 1000 ppm. So just displaying CO2 concentration, which is a proxy for ventilation, and the only source of this in indoor environments is, well, humans. So this is a very good starting point to give us an idea. But of course, other parameters, other pollutants can also be measured, can be displayed. And this would be a very good idea to awareness and keeping accountability. So I'd like to close with this image, which I liked very much, from the last year's November issue of the Scientific American, talking about the 1918 flu, which killed millions and then faded from collective memory. Will the same, or could the same, happen to COVID? Well, I'd say it's very likely that it will happen to COVID in another, maybe not 1 year, maybe 2 years, maybe 3 years. We will not talk about COVID anymore. But what we hope is that this pandemic will influence that shift in combating indoor respiratory infections. And we compared this, that's what should happen on the scale of the Chadwick Sanitary Report in 1842. And I'm sure you've heard about this well, where Sir Edwin Chadwick led the British government to encourage cities to organize clean water supplies and centralized sewage systems. Well, we need to have clean air supplies in our buildings. So with this, I'd like to thank you for your attention.
Well, thank you very much for that very comprehensive review of your work, which has opened up all sorts of thoughts in our minds as to how to control our own activities from day to day in our contact with other people. I would like to ask, have we got any questions? I think we have, haven't we?
We do, yes, we do have some questions. and we're sort of running a little bit over time, but I think we can fit them in.
Yes.
And I think the first one we could ask is, how long does, so David Ashworth has asked, how long does the virus particle in the air remain infective? Do you have a duration or in general?
Well, this depends on the environment, and this type of viruses, they like dry and cold conditions. So in environments, and that's often conditions generated in air conditioned buildings, very dry and cold. In such environments, they can stay infectious for quite a long time, even up to hours. The point is that the fact that they stay infectious for hours, they would probably, under normal circumstances, be ventilated if we are talking about hours. But if there's an infected person and keeps exhaling or emitting there, so for hours there will be the presence of these viruses. Now, if in humid environments, the more humid it is, the faster they will be deactivated. There were talks about whether we should humidify the interiors for the purpose of deactivation of the virus. Well, if we keep the relative humidity level at the level of the comfort, normal comfort for people, which is between 40 and 60% of relative humidity, this is already quite efficient in terms of deactivating the virus. But on the other hand, we can't say that if we increase the relative humidity to 80 or 90%, which would deactivate the virus faster, but it would create extremely uncomfortable conditions for people. So this wouldn't be a good solution. And again, this virus, the temperature in which is very fast deactivates about 50 degrees Celsius, but we can't have the temperature like this. So keeping humidity and the temperature at the level comfortable for people and not having it too dry or too cold, it's something which is already quite good in terms of the virus.
Thank you.
Could I just, I have seen that the question from Beverly about rhinitis and mucus production and how that would affect the distribution. I'm just trying to find it again. Where are we? Have you got it there?
Yes. So Beverly's question was, how is particle production affected by excess mucus production? For example, in allergic rhinitis.
That's going to affect the viscosity of the fluid, isn't it, Lydia?
That's exactly right. Everything which changes the viscosity, everything which changes the excess the mucus, it changes the production. So there've been even papers showing that if we do something like, for example, inhale something which affects the mucus, then it affects also the production of the particles. And the idea is that doing it this way, we could suppress particle production. But yes, as I said, that's the viscosity, that's the immediate impact on particle production.
Yeah. Yes. One thing that has been going around in my mind for some time is, and I think I mentioned it to you in one of my emails, the relationship between surface area and volume. And I think you alluded to the fact that small aerosol particles have a higher load of virus than larger aerosol particles. Is this related to surface area to volume ratio for a given mass?
Well, the reason that smaller particles have more of this virus, and then I was talking specifically of this virus, is because these smaller particles are generated in the deeper parts of the respiratory tract. So if that's where the virus is located, so it's aerosolized with these particles generated there. And if the main location of the virus is not the mouth, and that's where the biggest particles are generated. So therefore, the load of the virus in these particles is smaller. So this is really related to where it is, where the particles is coming from, and where is the virus located.
Yeah, I see. Okay, David, another question?
There is one from Heather, which is interesting. So what are the temperature effects on the aerosol and pathogen within? So in other words, will the temperature effects actually influence how long a virus is pathogenic? That's a difficult question, actually.
Yeah, I think I've tried to cover it in the previous response. I said the temperature and relative humidity. So yes, increase in temperature definitely leads to faster deactivation of the virus. So let's say that if we have the conditions like, well, very often here in Australia, temperature outside temperature 30 degrees or something. So this is definitely deactivating the virus much faster than if the temperature was 15 degrees. So yes, this has an impact.
Okay, thank you. Okay, I think that's probably all the questions we have time for. I think there are a couple more which overlap a little bit with what's come before.
Let's take that one. Let's take one more. And I want to make a parting shot, actually, but do that first.
Okay, let me just find it again then. It was to do with, well, yeah, again, it was Heather, actually. Do you have a view on naturally ventilating buildings by design versus
mechanically ventilated?
Mechanical, yeah.
This is a very good question and very important question. Well, on the one hand, ideally, we would say that we would like to have naturally ventilated buildings because natural air is better. Mechanically ventilated system create lots of problems. So from one angle, this is the best. But the problem is that in naturally ventilated, when buildings are naturally ventilated, and when the temperature outdoor is low, therefore, we are not going to sufficiently ventilate these buildings because we are bringing cold air. So therefore, the windows are closed, and as a result, we don't have the ventilation. There's another aspect of this. If outdoor air is polluted, like, for example, during the bushfires, we had examples of this during the summer a year ago, when a fire alarm was activated inside because of the smoke outside. So we want to do everything to prevent this pollution coming inside. So if we have natural ventilation, so we can try to seal everything, but then we have no ventilation. So the only way for this situation is to mechanically ventilate the building and filter the air, so then the pollution doesn't get inside. Now, there's also the aspect in all of this of energy, because if let's say we are bringing the air inside, but if it's cold outside, we need to heat this air. So we heated this air, we spent energy on this. Now, if we remove this air and bring new air, then we again use the energy. If, however, we have mechanical system and we recirculate the air, properly filtering and cleaning in between, so we save a lot of energy. So I'd say it's not as simple as saying let's have natural ventilation, because it may end up not having enough ventilation and using too much energy. So we really need to have buildings flexible to be able to use natural ventilation when possible, but if not possible, or if not convenient, or if not practical, be able to use mechanical ventilation.
And I think one final question relating to all your answers, really. This is from David Ashworth. What part does ultraviolet play? Is that something that you've considered?
Yes, in this, there was that one diagram when I talked about engineering solution, that starting point. is that I mentioned air filtration and disinfection. And there was under the graphic, you see that there is a UV lamp. That lamp is in that top close to the ceiling. Yes, it plays a role. So let's say if we can't do anything else in terms of cleaning the air, this is a way of doing this. UV system can be in the whole ventilation system, and that's where the air can be disinfected. If this is not possible, if we are talking about naturally ventilated building and it's not the circulation of the air through the mechanical system, the UV lamps can be close to the upper part, close to the ceiling, provided that the air is sufficiently mixed, that it goes there and it's disinfected there. So definitely this system have roles in terms of deactivated pathogens in indoor air.
Okay, thank you very much.
Could I just throw in one final question, please, David? Lidia, what is your view of blow hand dryers in public places in relation to what we've just been discussing?
Blow hand dryers.
I mean, you don't see them in hospitals, you don't see them in research establishments, but you see them in public places. So when and the air is blown out, it isn't drawn through a filter and then excavated and then blown out. If you wash your hands, you've still got bacteria and other microorganisms on your hand, however well you wash them. And the hand dryer just blows them into the atmosphere for everybody else to sample. That is my thought. So I would have thought that there would be a good case for banning them from now on after this last experience that we've had over the last 2 years.
Well, in principle, something like this is possible. But all the evidence so far is showing that anything on the transmission from the hands or from the surfaces is insignificant. So I probably wouldn't worry too much about this being something to mitigate.
But if people are in close contact when you're in a lavatory at the motorway or something like that. So you know, the distance is not very far away from somebody who is blowing.
Well, there's much more virus coming potentially from the mouth and nose than from the hands. So if we really were to worry about what gets into the air, we would need.
Yeah, but you're breathing into that airflow.
To put mask on the people. That would. I'd say this is potentially, but this is a very, very minor source compared to what we exhale.
Oh yes, of course, yes. But surely we should take all precautions that might lead to increased risk of infection. That's all I'm thinking. Yeah.
Okay.
Okay. Thank you.